Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 57 and in this we will be looking into the introduction of quantum metrological and its mathematical formulation at a later date. So, the outline of the discussion is of this lecture will be introduction to quantum metrology, which means the sensing mechanisms and what are the various areas of quantum metrology. Then what is the difference between a classical and quantum standards which we set in, various principles of quantum metrology and the limits of measurement in terms of resolution. So, this will be the outline of this world. Now, quantum metrology actually means sensing, right? Sensing state. Now, that state is state of a qubit maybe. However, the problem, as I also discussed with you earlier, that the sensing should be such a manner that it should not change the state of the system, and this will improve the measurement accuracy of any closed loop system. If you look at this is the object of measurement here, which is shown here, right, and you have the reference standard here. So, this standard is sort of, let us suppose a bit data is a reference and you get a object of measurement is ax. So, you are basically comparing this ax state of a quantity to a reference, right, considering a reference to be as the standard state. It is something like this, that let us suppose I want to measure a dimension of a particular object, then my reference is basically, let us say, volume of maybe a 1 meter by 1 meter by 1 meter, maybe a volume is my benchmark. Or I, in the linear scale, if I do, then let us say I have a scale of length 1 meter, and with respect to that I try to measure the object of measurement. Now, obviously, the accuracy of the measurement cannot be better than the accuracy of the standard, right. So, the standard obviously will have the best accuracy of measurement, but the object of measurement which you do actually should be as close to the standard as possible. So, you need to do two things as far as metrology is concerned, that you would like to make your Ax as closer to a reference as possible. This A reference might be the state of the qubit, right. This might be the state of the qubit which we are talking about, and the measured value is from the measurement is from the Ax is from the object of the measurement. Now, the people who are working in this domain, they are developing standards based on fundamental physical and atomic constants. Now, the constraint, as all of you know, is basically the uncertainty principle, the Heisenberg's uncertainty principle that will be applicable in quantum metrology. And these standard measurement units has to be realized using typical quantum phenomena as such. And therefore, the final goal is actually to replace the classical systems, right, standard systems, with the newer atom based systems. So, the final idea is basically this part with a quantum based system which we are trying to do. That is my final aim as far as quantum computing is concerned, right. So, please understand the metrology or the sensing will be done or should be done taking into consideration the quantum phenomena. You cannot take the classical phenomena into consideration for measuring these standards, because they will not be working in that domain of working, and therefore, we need to always work into quantum phenomena. Now, one methodology, I will give you a brief example which will make it clear. Say for example, if you remember in your class 12, you have been told about hydrogen atom problems, right, and there is a quantum well which is associated with it, there is a quantum well which is associated with it, and the discrete energy levels are available to you. Now, how will you measure that an atom has moved from one discrete level to another? So, by giving particular energy, you will see an absorption will happen whenever the input energy is exactly equal to the difference in the two energy states. This is a quantum mechanical way of measuring that if E2 minus E1, this is, let us say this is E2 and this is E1, then E2 minus E1 is effectively hc by lambda or h nu, right, which tells me that if I shine a light of say a particular lambda or I put a frequency of a particular width, I will see a certain absorption of the light, and absorption of light in that lambda will see that there is a transition from E1 to E2. So, this is one of the methods by which we will be able to extract the information that there has been a transition from a lower energy level to a higher energy level. Now, what quantum phenomena will you utilize in specifically case to quantum cryogenics is basically entanglement, which we have studied in our earlier lectures, tunneling and superposition, right. Entanglement, we already know what is an entanglement, that this is basically an action at a distance sort of. Superposition means two states can be in a superposition state with their appropriate weight attached to it. And what is tunneling? Tunneling is basically that if you have, say, an energy barrier and you have a particle which is coming at this end, this is a particle, then the probability in classical world is probability of finding this article at this particular point is 0. So, the probability will be 0 at this edge, right. However, it will not be 0 if it is a quantum mechanical world. So, there will be a finite probability that it will basically transmit through this within this barrier and reach here, and therefore, if you want to find out this psi star, the wave function derivative, then this will not be equals to 0 at, say, this is A. Then at A it will not be 0, it will have some finite value. Now, this proves that there is a finite probability that even if the barrier is there, the electrons or any particle, small particle electron can tunnel through that barrier and reach the other side, and this is known as tunneling, right. And there are other tunnelings also, for example, band to band tunneling, BT we refer to in a case of a tunnel FETs, right. In case of tunnel FETs we do it, right, FETs we do it, and then there are other gate leakage tunneling, direct tunneling, and so all those Fowler-Nordheim tunneling is there. But please understand, the important point is there is an energy barrier, you try to tunnel through it from a lower energy to the other side. Where do you find the applications? You find the applications in atomic clocks, right, and in junctions where we use Josephson junctions, and quantum effects is the point where we use it, and all these are at low temperature, kept at low temperature. So, we need to again focus on defining our SI units using quantum standards. That is the major concern which we have as far as quantum mechanical condition is concerned. So, let us see what are the areas where you need to bring the quantum standards very close to the physical unit. So, one of the example is voltage in a Josephson junction is one of the examples where you do it. Then you talk about resistance in a quantum Hall effects, and then you look into atomic clocks when you want to do a time specific measurements. And then obviously the laser based standards are there, which are also there. So, this is for the length, right, this is for the resistance, this is for the voltage, and this is for the time domain. So, the basic units in SI systems, which are voltage, resistances, or time or length, needs to be converted into corresponding quantum mechanical standards, and which should remain stable for the whole measurement, the domain of measurement, the time domain of measurement. Now, as I discussed with you earlier also, that the ultimate limit of measurement precision is Heisenberg's uncertainty principle. What does it tell me, Heisenberg's uncertainty principle? That the difference in the space and its momentum should be greater than equals to h by 2 pi. Let us keep it equal, then let us suppose this is equal to h by 2 pi. Then if you are able to measure with absolute certainty where your material is at a particular point, then you will not be able to properly understand the change in the momentum. Similarly, if you are able to predict precisely the change in the momentum, you will not be able to check what is the value of delta x, which is the space limitation. And that is what you need to understand or get the point, that two things cannot be done in exactly the same manner, and there will be always an uncertainty. If you are able to predict one of the parameters with certainty, the other parameter shows an uncertainty over a such that if you multiply both of them together, that should be around h by 2 pi. Now, so this helps you to create the highly sensitive electronic components in SQUID. This is known as superconducting quantum interference devices, and they are used for magnetic sensing as such, right. And then you have single electron transistors here, and these are for precision electronics, because we are actually looking into movement of a single electron within the transistor, and therefore its accuracy is very high, and therefore it is very useful for all precision electronics, or where the accuracy of the measured output should be the highest. Okay. Now, let us come to the difference between classical and quantum standards. Now, classical standards offer universality and stability, right, which is not achievable from classical standards. And the point is that the quantum standards which you generate is universally applicable, and the stability is also universally applicable, but that is not true for classical standards. Similarly, classical standards are defined by physical artifact. For example, you are doing a meter bar or a kilogram, whatever the prototype which is there with you. So, these are the standard kept at very regulated temperature and regulated physical parameters are maintained, and that happens to be a benchmark in a sense. In quantum, we do not do that benchmarking in that way. Similarly, in quantum what we do is based on constant, for example, Planck's constant, elementary charge and so on and so forth. And another example is Josephson effect, where we consider the voltage standard. So, what we do is we look at the physical artifacts as well as we look at the quantum artifacts. Then we are trying to see which one is more stable and which one is more properly benchmarked in terms of standards. Now, let us see, if we look at supercomputing, classical computing and quantum computing, if these are the three sort of columns which we have shown here, then based on certain parameters or template parameters, can we predict what should be the value of the, or can we predict a priori which has got a more advantageous position as compared to another. So, let us look at unit of information. Of course, in unit of information, classical computing is bits, right, we all know that. Supercomputing is also bits, and but for quantum computing we use qubits. So, this is a very basic one. Possible states are 0 and 1, right, 0 and 1, and here what quantum computing comes into picture, it's not only 0 and 1, but the superposition of 0 and 1 states, right. Calculations are deterministic in both classical and computing, supercomputing, right. Why it is deterministic? Because there is no chance of having any probability coming into picture, which happens in case of quantum computing, and therefore there is a multiple possible outputs are there for the same set of inputs, right. For the same set of inputs you will have multiple possible outputs available to you, and in classical it is always deterministic, as you are aware of. So, calculations are very deterministic in classical computing, but probabilistic in quantum computing. Let us look at data processing. All of you are aware of, this is a binary logic which we use a binary logic in sequence or in parallel, and in quantum computing we use quantum logic in parallel. So, this is not sequential in nature, they are parallel in nature. If you look at the operations, basically as you all know, it is a Boolean algebra which we do for both of them, and here we do linear algebra or over a Hilbert space. So, my Hilbert space is the space where we do the computing in quantum. Circuit behavior, of course, we all know these are classical physics based, and this is based on quantum mechanics. So, your circuit behavior can be probabilistic in nature when you actually work with quantum computing, right. The typical number of processors which you use are 1 to several for classical, but for supercomputing there are large number, thousands to million number of processors. You can, not million, but large number of processors can be used. Quantum typically has one. Typical environmental conditions, if you look, for traditional classical computing you do not have to be too much constrained on the temperature front, but if you use supercomputing, needs to be temperature controlled data centers, and if you work with quantum computing, extremely cold cryogenics has to be maintained, or refrigeration has to be maintained in order to have the computation in a proper fashion. Now, we all do this quickly, we will go through it and see how this works out. Now, what we saw was, and this is quite interesting, that the black body, which means if you have a black body and there is a radiation coming out of the black body, it does not come out in terms of continuous wavelength, it comes out in discrete value, and that introduced sort of an energy quantization in order to resolve the black body radiation as well. And how was it involved? That each packet, the energy is quantized into h into nu, right. This is generally written as E equals to h into nu, where nu is the frequency of the input radiation. Now, this input radiation may be optical or otherwise, right, and that resolved the ultraviolet catastrophe in a nature, and this led to Planck's radiation law. These are very old laws and have been validated in the classical and quantum world to a larger extent. Then came Schrodinger equation and wave function, and this basically describes how a quantum mechanical system will evolve over a period of time. And one of the time dependent formulas is shown here in this case, right, and this is, so this psi is basically my wave function, which is a function of both space and time, and therefore this as I discussed with you earlier, my psi square, right, gives me a probability of finding a particle within a space. So, if you do like this, and if you integrate this psi star which is exactly equals to psi mod. If we integrate it d psi, then if we do it from minus infinity to plus infinity, this will be exactly equals to 1, because the probability of finding the article from minus infinity to plus infinity will always be equals to 1, right. And therefore, this in a sense gives you a brief idea about the Schrodinger equation and the wave function, right. Now, Pauli's exclusion principle, these are the basic fundamentals of quantum mechanics. It tells me that no two fermions can occupy the same quantum state. Why we are discussing this is, this will help you to understand what are the limitations of quantum measurements, right, because in any case when you do a quantum measurement, these exclusion principles and everything else will always come into picture. Obviously, they explains the structure of the periodic table, and therefore, the atomic level energy configuration is done using the Pauli's exclusion principle. The most important part of Pauli's exclusion principle is that no two fermions, for example, the electrons in this case, can occupy the same state, quantum state, the same instant of time, right, and two fermions can never occupy the same quantum state. Okay. We have already done this, and this is interesting results which we have found out, and this is basically what is known as the Heisenberg uncertainty principle. If you look at this expression, which is given as delta x dot delta p should be greater than equal to h cut is nothing but h by 2 pi, h by, so this will be h by 2 pi, h cut is h by pi 2 pi, and this tells me that accuracy of, as I discussed with you, position and momentum don't hold the accuracy. There is also another Heisenberg uncertainty principles, and that is delta E dot delta T should be greater than h by 2 pi. The delta E is the accuracy of finding the energy, and delta T is the time, exact time which you are trying to measure from that particular point. And this impacts therefore the atomic scales measurement precision, and this gives you a brief insight into that even with atomic scale there will be, you cannot go below this, but in reality as a designer or as a quantum mechanical designer for qubits and its measurement system, this does not worry us too much, because the values are so small in nature. This is approximately, if you remember, this is approximately 10 to the order of 10 to the power minus 34, and so they are so small that though it implies it's an important world, but the value, absolute value, is relatively very small. Now, as I discussed with you, therefore, that quantum effects actually impose resolution limits in the precision measurement. When you do a very heavy precision measurement, the resolution actually limits the measurement techniques. As I discussed with you also, again the thermal power spectral density is given by this expression, and then at low frequency the thermal noise dominates, and at high frequency quantum noise dominates. So, we need to also therefore have a boundary value problem where we know that below which frequency does my low frequency and above which frequency is my high frequency. We should be able to dominate that. At low frequency, as I discussed with you, we will have thermal noise will be more, and at very high frequencies the thermal noise will reduce, because thermal noise is almost like 1 by f, and high frequency the quantum noise dominates. And these are electrical noise I am talking about, these are not physical or other noise, these are electrical noise which we are talking about, right. Okay, let us see what is the key to the quantum sensing technology and what are the real world applications which we will do in such a scenario. Now, if you look at certain definitions of quantum sensing, the first definition is, as I discussed with you, using a quantum states, you will know that discrete energy levels to sense the quantum quantities. And how you measure it, that measurement technique relies on quantum coherence formula, and basically depends upon the superposition of states, and this leads to a very precise measurement, with the caveat that uncertainty principles will always give you a limitation in terms of measurement. And as I discussed with you, quantum entanglement helps you to surpass the classical limits. So, if your classical limit set at x, then the quantum limit is much smaller than that in a sense, right. And why is it so? Because the entanglement and superposition helps you to generate large number of state space, which will give you much more accurate values of the measured quantities. Now, let us look at the quantum sensing, and therefore, as I discussed with you, this gives you an enhanced value of sensitivity and precision compared to classical sensors, as I discussed with you, entanglement and tunneling, and it is extremely precise measurement and operates beyond the typical classical sensitivity limits, right. We have already discussed this point once again. Now, let's look at the 4 key attributes to a quantum sensor. If you want to sense anything, what are the 4 key attributes which you need to do? First is 2-level quantum sense system. right. So, this is basically a 2-level quantum system which I am referring to here. Now, the sensor must have discrete and resolvable energy levels. So, if I say this to be a state 0 and this to be a state 1, then I say that the energy which is required to push from state 0 to state 1 is given by h cut into omega naught, right. It gives you h cut into omega naught. And similarly, the corresponding value of the energy required is to move from 0 to 1 or 1 to 0, the energy amount released will be equals to h cut into omega naught, where omega naught is the frequency which you are seeing. Now, then the second part is basically, so the first is a 2-level quantum system which you are going to generate. The second is state initialization and readout, and therefore, so you see, if you want to read something, you need to first initialize your state, right, and state initialization reliably is a very important part, which means that you are reading the initial state properly, then only you can be able to understand what is the final state, which is the measurable quantity. And therefore, both state initialization and readout are quite critical for quantum sensors. Now, coherent manipulation, if you look, it should be possible to control the quantum state using external field, right. Obviously, because if you are not able to do it, most of the protocols, at least for sensing protocols, if you are not able to do this, you won't be able to understand typically what is happening within the quantum system, especially a qubit, for example. So, how we do it? There is an optical method as I discussed with you, and there are RF pulses which you can send it to the qubits. When you send the RF pulses, they reflect back, and then you try to read from the reflected RF pulses what is the state of the qubit. Now, interaction with an external quantity is my fourth one, and the system must actually couple to a target physical quantity. For example, the measurable quantities are current voltage, and they manifest in terms of electric field and magnetic field, and therefore, there will be a transition energy which will be available, which will change the state via a sensitivity factor which is referred to as gamma, and this is basically del E q to del V in this is gamma, and typically my gamma values are 1 or 2 which you get, right, and quadratic. If it is a linear, then I get 1, if it is a quadratic I get 2 in this case. Now, what are the basic methodologies for quantum sensing? First is, as I told to you, the 3 steps are basically sensor initialization. I need to initialize my sensor properly. They need to interact with the signal without, please keep in mind that this should be done without changing the state of the system. So, you need to initialize the sensor, right, first of all, then interact with the signal, and then once you have interacted, the sensor readout and signal estimation needs to be done in the output side. So, sensor readout and signal estimation needs to be done at the output, and this whole thing we were discussing during the previous lectures. So, we were more interested in this topic, and we had discussed, most of the discussion was centered around this one, that how do you estimate the signal, and once you estimate the signal, how do you manipulate the signal at your output circuit so that you are able to extract the value of the state of the qubit which they are currently in. Now, there are many sensing technologies available. These are NV centers in diamond, right, non-volatile centers in diamond. These are ultra sensitive magnetic field sensors. These are primarily magnetic field sensors. Then there are atom interferometers which are used for gravitational and inertial sensing. Then there are quantum gyroscopes for measuring navigation without GPS. Precision navigation is done, and optomechanical sensors, because of small displacement, if you use a quantum light, then there is a small displacement or a force, then we define that to be as the optomechanical sensor, and gives you a brief value of the various quantum sensing technologies. Now, let us look at the real world applications. The real world applications are in healthcare, right. So, brain activity mapping, MRI enhancement. In terms of navigation, GPS, free inertial navigation for submarines or spacecraft, geophysics for underground exploration via gravity mapping, defense and security, stealth detection and quantum radar, and fundamental physics will detecting dark matter and gravitational wave. So, these are the few real world application which needs to be taken into account. So, let me recapitulate about what we did in this half an hour of our lecture. We actually went through the various mechanisms of quantum sensing. What is the meaning of quantum sensing and metrology? So, we understood about quantum sensing and metrology, right. We then looked into limiting factors of quantum sensing, limitations of quantum sensing. Then we looked into the 4 methods of sensing, and finally we understood the various applications of sensing in healthcare, right? We looked into healthcare, in defense and security, and so on and so forth. There are many applications which I have noted it down. And so this gives you a brief insight about how you sense the quantum sensing mechanisms, right? So I hope you enjoyed this lecture, and till we meet next time, goodbye.